In this lesson, we're going to examine how we can set up word problems to be solved. We're not actually going to solve any today. Just want to worry about the setup. So once we figure out the setup, we'll learn some methods we can solve them. But generally, like in trigonometry, the setup's the hard part. So to start, we're going to figure out some words, some things that we should know about. So we see the word, we see a plus sign. What can a plus sign represent? Well, some common words we know go with plus signs are add, and the word sum in math always means that. You may come across the words more than, increase by, together. These are just some examples, and we'll come across some more as we're doing some word problems. So we may have to add to the list. Okay, obviously this could be minus or subtract. Right? But the word difference, that's a mathematical word for minus, the difference between two things. You could have less than. You could have decrease by. Here's some examples. Obviously, this could be the next example. We could have times or multiply. Those are kind of our standard ones. In math, the word product means multiply. You could have the word multiple even. You could have time doubling or tripling. And it's a multiple of something. You don't see too many different words that we'll come across for that one. If we look at dividing, what does dividing mean? Well, obviously divide, or divide by if you want to. The math word for this is quotient. You could have the word fraction, it's a fraction of something. You could have words like halving, a third of something. And again, there's not too many there. And of course, we have the equal signs. So equals, most often we'll see the word is, right? Comes out to, gives. Those are all words that means equals. And so our challenge today is going to be taking English and turning it into math. You got to take words and turn them into symbols. So let's take a look. Numerical, non-unit. Okay, so we're going to come across some situations where we don't have units that are numerical problems that we need to solve. Every word problem we set up is going to follow the same sort of procedure. We need some let statements, the things we don't know. We have some variables. The things that we don't know are, right now, they're x. So if we look at the first example, the larger of two numbers is 4 times the smaller, and their sum is 85. Find the numbers. What don't I know? Well, I don't know the numbers. So why would we not let x equal the first number? In this case, it's a large number. And we can make y be the small number. If you did vice versa, it is not going to make a difference. Your equation would just be the opposite of mine. And again, we're not solving them. We're just setting them up today. So the larger of two numbers is 4 times the smaller. In other words, x is made up of 4 y's. That's an equation. We also know that the sum is 85. Sum is the word add. Is the number equals. So in other words, x plus y is equals 85. And that's it. That's all I want you to do today. Okay? Set up, so give me some let statements, make me an equation. Okay. Let's try the next one. The sum of two numbers is 39. Twice the first number plus 3 times the second is 101. Find the two numbers. Okay, so I don't know what they are. X, in this case, it's going to be my first number. It doesn't tell me I have a large one or a small one, so I'm just going to call it first and second. What do I know about them? Well, I know right off the bat the sum is 39. If I add them together, I'll get 39. That's not too bad. I also know twice the first number, so 2x's, plus 3 times the second, 3y's, is, here's my equal sign, 101. Oh, I've got two equations. And again, I don't want to solve it, just set them up. Now, try the next side. The next type goes back to grade 9. We call these break-even questions, when two things come out to the same value at some point. And the reason we use the words break-even is we talk about money. When you break even, your costs equal your revenue, and you're making no money. Okay? So in this question, we have Hank. He has two different job offers to sell furniture. The Brick offers him $280 a week, plus he earns 4% commission. Reed's offers him a little bit more than each week, but his commission's lower. So we need to talk about commission first of all. Commission is a percentage of sales. In other words, you have to take your percent, turn it into a decimal. Let's look at the Brick for a second. So 4% of the decimal is 0.04 for every dollar that he sells. That's what we don't know. So X is our number of sales, or I guess it should be value of sales, not really number. You sell $10 worth of something. Value of sales. And the more he sells, the more he's going to earn. He sells $1,000 and gets 4% of that. It means he made $40. He sells $10,000, he made $400. Right? He gets a percentage of his sales. So in this break-even question, and as most break-even questions are, it's not necessarily two different equations. It's usually sort of like two different companies or two different situations. So the Brick. From the Brick, he's going to earn automatically every week $280. The weeks aren't really a variable because both companies you have to work the same number of weeks, right? It's not a variable. But he also gets 4% and turned to a decimal of his commission. Sorry, of his sales. Reed's, on the other hand, is going to give him $350 a week, so he starts higher, but he only gets 2.5%. So as a decimal, it's 0.025x. And at some point, even though he starts at a lower value at the first company, at the Brick, because he's earning more per commission, he could earn more from this company. These two lines will cross somewhere. As we talked about previously, if your slopes are different, in this case your percentages, they will meet at some point down the road. And I don't care today where they meet, I just want to know that they will meet somewhere. Okay, that's kind of our standard grade 9 question. Here's our standard grade 10 question, mixture problems. A mixture of two things. So I have three situations we're going to look at, kind of standard ones. One's involving percents, one's involving values, monies, and one's involving kilograms or weights of things. All different kinds of mixtures. And they might sound different, but they're all set up in roughly the same way. Let's take a look at the first one. George has a total of $155, consisting of $2 and $5 bills. He has a mixture of them. If he has 40 bills in total, how many of each does he have? Well, the fact that it's asking me how many does he have tells me my let statements. X is the number of $2 bills. And I'm going to make Y the number of $5 bills. Now, I don't know how many of each I have, but I know I have a total of 40 bills. And that's made up of some $2 bills and some $5 bills to give me 40 altogether. That seems pretty reasonable. The second question deals with the second equation deals with the value of them. For every $2 bill I have, I get $2. So if I had, I don't know, 9 of them, I'd have 9 times 2 gives me $18, right? So in other words, I can say that I have $2 for every one of those that I have, 2 times X. And for every $5 bill I have, I'll get $5 for every one of those I have, multiplied by 5. And I know I have $155 in total. And there's my two equations. One based on how many things I have, and one based on the value of the things that I have. And that's generally how mixture problems are set up. One based on number, one based on value. Let's take a look at the second example. A $2,000 prize was invested at 9% and the rest at 10%. That's how much money they earn on their prize. The total interest received was $191. How much was invested at each rate? Well, I don't know. I got to figure that out. X is the amount at 9%. I would be the amount at 10%. You might ask yourself, the amount of what? Well, it's the amount of the prize, the $2,000. Well, if I'm talking about the $2,000 and I've got some going in at 9 and some going in at 10, that tells me that together they have to make up that $2,000. There's my equation. I also know that the value I get, I earn 9% for every bit I put in. Well, 9% as a decimal, the value of it is 0.09 for every dollar I put in. Plus, I earned some at 10%. So I get 0.10, or just 0.1 if you want. Why? And the total amount of interest I earned was $191. So like the last question where I had $2 for every number of these, now I'm getting 9% for every amount of these. It's the same idea, just different format, different words. Let's try the third one. Pets R Us sells premium dog food, $15 a kilogram. Basic dog food, $10 a kilogram. They want to mix the two together to create a new mixture that's going to be sold for $12 a kilogram. But what don't I know? I don't know how much the kilograms of each. The kilograms of premium and the kilograms of dry. Those are the two things I don't know. But I know together there's 100 kilograms. My sort of standard basic equation, the first one. I also know that the value of a premium kilogram is worth $15. So it's 15 for every kilogram I have. I know the dry dog food's worth $10 for every kilogram that I have. And I know that my overall mixture is $12 for every kilogram that I have. Now here's a trick idea. There's 100 kilograms. So if it's $12 per kilogram and there's 100 kilograms, my overall value has to be $1,200. So in this case, they didn't tell us, like they did at the beginning, you got $155, you had $191 in interest, but we could really easily figure out the overall value of $1,200. That wasn't too tricky to do. And there, I'm done. I've set it up. Today's all about the setup, right? I'm not trying to solve them, just set them up. All right, last one. Rate problem, or distance, speed, time problems. When I come across a distance, speed, time problem, my suggestion is to set up a table. Tables organize your information, much like diagrams do. And distance, speed, time questions have kind of the same standard table. They have distance, speed, and time, and generally you can have two parts to your problem, and then a total. If you look at this first example here, we have John. He's traveling from Detroit to London at a speed of 80 kilometers. Then he goes from London to Toronto at a different speed. So the two parts of the problem are Detroit to London, and then London to Toronto. And usually we are going to know four important pieces of information. Right off the bat, I already know his speeds were 80 kilometers an hour and 100 kilometers an hour. If you keep reading, the whole trip is a distance of 600 kilometers. Well, that's his total distance, and it took 7 hours. That's his total time. I want to write two equations that represent the situation. And I'm going to point out, you can't have a total speed. There's no such thing. You get an average speed, but you can't have a total speed. So get rid of that box. That leaves me 4 boxes. 2 of them we're going to fill with variables, x and y. And we're going to fill them based on our idea of distance equals speed times time. Distance equals speed times time, which is one of those little science triangles you probably looked at last year in grade 9 science. If I put x here and y here, then my distance, which is speed times time, has to be 80x. These two things multiplied together. And similarly, these have to be 100y. And now I can get my equations. My equations come from this table. They come from the columns. Part of the distance was 80x. Part of it was 100y. Altogether was 600. So in other words, 80x plus 100y equals 600. Part of the time was x, part of the time was y, the total time was 7. So in other words, x plus y has to be 7. There's our equations. This table makes my life really easy because it organizes it and it gives me the equation without having to do a whole lot of thinking. And last one. When Arthur goes fishing, he drives 393 kilometers from Ottawa to a lodge near Temagami. He travels at an average speed of 70 kilometers an hour along the highway to North Bay and then at 50 kilometers an hour on the narrow road from North Bay to Temagami. It takes him 5.5 hours. Make two equations. Okay. Distance, speed, time. All right, what's part one of the problem? He needs to get from the highway to North Bay. Okay, so he's going to go from Ottawa to North Bay, and then from North Bay to Temagami. Okay, and our total. What do we know? We know that there's 393 kilometers total distance. We know he travels an average speed of 70 to North Bay. We know he goes 50 on the narrow road next. It takes him 5.5 hours to make the entire trip. Okay, we know we can't have an average speed, or total speed doesn't exist. Times should be x and y, which makes this 70x and 50y. And then there's our equations. 70x plus 50y has to come out to 393 kilometers. X plus y has to be 5.5 hours. And there's our two equations. And those are our basic word problems, how to set them up. And today's homework is a handout. And we're going to just do the even numbers or the odd numbers. Pick one or the other. I'm not really picky which one you pick. We can do half of them. Practice setting them up. That's our objective today. Okay, so let statements and the two equations. And there should always be two equations and two let statements. And if you're stuck, we're going to keep practicing these because we're going to be learning the techniques to solve them over the next couple of days. And we'll do an assignment just on these. But come in and see me if you're already stuck.